Of the 5 logical connectives that we're going to meet, here is the second one, or. So the symbol for or is this an upside down version of the symbol for and. It's this V shape. And if you have a proposition phi and a proposition psi, and you stick this between them, then you get a proposition. So this thing as a whole is a proposition. And that's it for the grammar of or. That's the full grammar rule there. This is how you would read it or write it in English, phi or psi. And there are basically 2 questions now that must be answered for how deduction works for this thing. One is if you know that phi or psi is true, so if you know that this is true, then what can you deduce from it? And another question is if you don't know that it's true but you want to prove it, then what would you need in order to have it be the result of your deduction? How would you conclude it? So basically, how do you prove it and how do you deduce from it? And it's much easier to describe how to prove it, so let's start there. The rule basically is if you want phi or psi to be at the end of your deduction, if you want to conclude it, then you must either have phi in hand or psi. So if you knew that phi is true, then you can conclude phi or psi is true. And if you knew that psi is true, then you can also conclude phi or psi is true. So you have 2 options as to how you can prove phi or psi. Let me give you an example of how this might work. So suppose that phi is this sentence, the cake is flavored with chocolate, and psi is this sentence, the cake is flavored with vanilla. Then suppose that when you look at the actual cake, you see that it is flavored with vanilla only. Let's say white is vanilla and red is chocolate. Then what can you conclude from this? According to the rules of or, so if you look at the cake and you see that it is in fact flavored with vanilla, that means you know that psi is true, right? The rules of or tell you that you may now conclude phi or psi is true. So by observation, we see that psi is true. Therefore, by the deduction rules for or, phi or psi is true. Hopefully this makes some intuitive sense, even though it feels a little bit weird to say this sentence once you know that psi is true. So it would make for strange conversation to say these things, but let's just suppose that someone, just wants a yes-no question, and they ask you, hey, is the cake either flavored with vanilla or flavored with chocolate? Then you can definitely answer yes, it is, in fact, either flavored with vanilla or flavored with chocolate, because it's flavored with vanilla. So that's the deduction that I'm describing here. Now, if it were flavored with chocolate, then it would work the same way. If you had phi, then you could also deduce phi or psi. What if it were flavored with both? So suppose it's half vanilla and half chocolate. Then what would you say about phi and what would you say about psi? Phi is true because the cake is in fact flavored with chocolate. Just look at it. Psi is true because the cake is in fact flavored with vanilla. Just look at it. So what can you conclude here? Can you still conclude that yes, the cake is either flavored with vanilla or with chocolate? Yeah, definitely you can, because the rules say if you have phi, you can deduce phi or psi. They don't say that you need to verify phi and not psi. They're just saying if you have either one, then you can deduce the or. You don't have to consider the other one then. So in this situation where the cake is flavored with vanilla and chocolate, the line of reasoning I'm describing here is valid. this is true by observation, and this follows. The cake is in fact flavored with vanilla. I don't care if it's also flavored with chocolate, and this follows. So that tells you something about the or in mathematical logic that might seem different from how we sometimes use or in English. In English, if someone says the cake is either flavored with vanilla or with chocolate, you would probably deduce that it's one or the other, but not both. But in mathematics, or doesn't work that way. It's inclusive. To say that phi or psi is true is to say that either one is true, or the other is true, or both are true. That's included. All right, so now I've told you how to... Sorry, the title here is wrong. Now I've told you how to prove phi or psi, but suppose you're not trying to prove it, in fact you have it. So maybe someone tells you the cake is flavored either with vanilla or with chocolate, and you want to use it to prove other things. How do you make any use of it? So that's a little bit harder to describe, and it'll require our first official numbered rule of logical deduction, and that's called proof by cases. So here's how the rule works. So to describe this rule is supposed to be about how I can use phi or psi to prove something else, right? So to describe this rule, I'm going to need to have something else in mind. Let's say it's a proposition omega. So say you want to prove omega, some other third proposition. And suppose you know that phi or psi is true. Then one way to do it is to do the following. If you can prove omega from the assumption that phi is true, and you can prove omega from the assumption that psi is true, then you can deduce omega from what you started with, from knowing that phi or psi is true. So when you know that phi or psi is true, at first it's difficult to draw conclusions from that, right? Like, you know that the cake is flavored with either vanilla or with chocolate. How can you draw any conclusion from that? You still don't know what the cake is actually flavored with. Well, any conclusion that you could draw, regardless of whether the flavoring was vanilla or chocolate, any conclusion that you can draw in the vanilla case and in the chocolate case, you can draw that conclusion in the vanilla or chocolate case. So that's the idea of proof by cases. So let me give you an example following the vanilla chocolate story. So let's suppose your friend is throwing a party for you, and they tell you that they have a cake, and the cake is flavored either with vanilla or with chocolate, and they're not telling you which. And also your friend is using mathematical logic, so of course it could be that the cake is flavored with both, actually. So that's what you know. You know the cake is either flavored with vanilla or with chocolate. Then your friend asks, "Are you going to like the cake?" Well, you think to yourself, let's suppose we're in the case that the cake is flavored with vanilla. Well, I do like vanilla, so then I would like the cake. Okay, now let's suppose we were in the case that the cake is flavored with chocolate. I do like chocolate, so in that case I would also like the cake. So then you can tell your friend the following proof by cases, since in every case I end up deducing that I would like the cake. With the information you've given me, just that the cake is either flavored with vanilla or chocolate, I can conclude I will like the cake. Now, there's a really particular format that I want you guys to write proof by cases. a particular format that I want you to use for writing proofs by cases. So let me use the cake example just to show you that format. And you'll use that in basically all of your proofs this quarter. Okay, so let's make these assumptions. Let's assume we know that I like vanilla cakes. That's number 1. And assumption number 2 is I like chocolate cakes. And assumption number 3 is the cake that my friend prepared is either flavored with vanilla or with chocolate. So here's how I would then prove this third thing, this omega, which is that I like the cake that my friend prepared. So somehow I need to make use of the assumption number 3. Well, I need to use assumptions number 1 and 2, which are just some propositions. But I also need to make use of assumption number 3, which is specifically an or. It takes the form, phi or psi for some propositions, phi and psi. So somehow I need to use this to prove the claim. To do that, I will use proof by cases. So here's a proof of the claim. Case 1. There's a case 1, and there's a case 2. So in case 1, I'll suppose one of the two sides of the or. So I know either cake flavored with vanilla or cake flavored with chocolate. So suppose the cake, and really I should write the cake that my friend prepared, but let's just say the cake for short. Suppose the cake is flavored with vanilla. Then, by assumption number 1 up here, I like the cake. Case 2, suppose that the cake is flavored with chocolate. Then, by assumption number 2 above, I like the cake. And if assumption number 3 has already been made very clear, then I could end the proof here and say we are done due to the rule proof by cases. But let me just clarify exactly why we're done here. Okay, so due to, by let's say 3, we have covered all the cases. You could write something like this. You don't have to write exactly this. We have covered all the cases since, assumption 3 says either the cake is vanilla flavored or is chocolate flavored. So we've covered the vanilla flavored case, and we've covered the chocolate flavored case, and in both cases we ended up with I like the cake. And we concluded in all cases that I like the cake. Therefore, I like the cake. So I can just draw that conclusion overall now. So that's proof by cases. Now I can end the proof and I can put a box or whatever symbol you like for ending proofs. It's now established that I like the cake from these 3 assumptions above. So that's proof by cases. And you don't have to follow the exact phrasing that I used, but there are some things that you should follow, at least early on, until you find acceptable other phrasings. So here's what you should follow. Numbering your cases and making them their own separate paragraphs like I've done here. That you should definitely do. And after the start of a case, you should definitely make clear what is the assumption for the case. So here I'm saying, suppose the cake is flavored with vanilla. It's important to use a word like suppose to make it clear that this is an assumption for the sake of a proof by cases. this was, a lot more wordy than it needed to be to demonstrate the proof by cases rule. So let me show you the same thing, but with the Greek letters serving as placeholders for things. So I'll be right back to show you that. Okay, so the first thing I did is I replaced 1 and 2, assumptions 1 and 2, by some things with Greek letters. And we have not actually introduced if-then yet, but just go with it. It'll still make sense, and it'll make even more sense later on when we introduce if-then. So 1 used to say, I like vanilla cakes. Now it says if phi, so phi is going to be the cake is flavored with vanilla, and omega is going to be I like the cake. So if the cake is flavored with vanilla, then I like the cake. That's a way of saying what was previously written. Let's say psi is the cake is flavored with chocolate. If the cake is flavored with chocolate, then I like the cake. So this is just like what we had said, what we had assigned to phi and psi earlier. I think I swapped vanilla and chocolate, but not important. Okay, so now number 3 is going to say either the cake is flavored with vanilla or it's flavored with chocolate. So that's phi or psi. Just like that, phi or psi. And the claim now is omega. Omega is I like the cake. So the claim is just that omega holds. And here's how the different cases are being handled. So case 1 says, suppose, so we know that either phi or psi, right? So suppose phi. By 1, it follows that omega. And then case 2, suppose psi, the cake is flavored with chocolate. By 2, it follows that I like the cake. Follows that omega. And then the conclusion is, since we concluded omega in both cases, since we deduced omega in all cases, we have omega. And then that's the end of the proof. And by have omega, when I say I have a proposition, I mean I have that it is true. I have that fact in hand. I have concluded omega overall. So, in other words, the claim here is proven. So that's proof by cases. Now, I would also like to show you just where that shows up in the notes. So here are the notes, and again, if you look at section 2.8, the summary for the entire logic section, you can see disjunction, that's the name for or, the fancy name for or, how to prove it and how to use it. And proving it is pretty simple. How to use it is proof by cases, which if I click on this, is described here under Rule 1. And here's not an actual theorem, but a template that you can follow for how a proof by cases is written. So this is basically the template that I was following.